So I have assessment 1 or assessment 5 in front of me, and we're going to start with looking at number 1. And I don't know why I am drawing that so big here. So number 1, we have deuterium and we have an amine. And on this carbon, we have a deuterium and we have an amine. Okay, so overall, I would say that you did better on the chirality of a molecule part than the RNS, and that's very typical, especially as you're just learning this. Okay, so let's start with chirality of a molecule. You do have a plane of symmetry that runs right through here. Okay, we also have 2 asymmetric carbons. We have one at the top here where we have an amine attached, and we have one at the bottom here where we have the other amine attached. But we do have a plane of symmetry. So we have 2 asymmetric carbons and 1 plane of symmetry. So therefore, we have a meso compound, which is achiral. It is not chiral. Okay, so let's look at the carbons. Let me bring up the chat here too, in case anybody has questions. All right, so I'm going to look at the asymmetric carbon that I put the little blue dot on. Okay, so attached to this carbon right here, I have a carbon, a nitrogen, a deuterium, and an oxygen. Okay, so I have 4 different groups attached right to that carbon. All right, no ties. So now I'm just looking for the heaviest atom. So oxygen, nitrogen, carbon, deuterium. What's the heaviest one? Oxygen, right? Oxygen's heaviest. So oxygen gets 1, followed by nitrogen, followed by carbon, and lastly is going to be deuterium. Good? All right, so I'm going to write that off to the side here. So I take a look. I have my lowest priority group, which is 4s in the front. So I can say, let's apply the opposite rules. If I go from 1 to 2 to 3, that would typically give me S, which means that this is R. I could also flip this over. And if I flip that over, then I would get 3 here, 1 here, 2 in the front, and 4 in the back, which would give me 1 to 2 to 3, which is R. So the blue one is R. Any questions about that? Okay, so let's look at the purple one. Luckily, it's the same atoms, right? We have a mirror plane in the middle. So we have oxygen, nitrogen, deuterium, and carbon. So oxygen gets 1, nitrogen gets 2, deuterium gets 4, and the carbon gets 3. So I'm going to draw that off to the side where I have 4 on the wedge, 2 on the dash, 3, and 1. Okay, lowest priority groups in the front. So we can do the opposite rules, which would mean 1 to 2 to 3. Normal rules would say that's R, so that means it is S. Or you can take it and flip it over so that the lowest priority group is in the back. When I do that, 3 goes here, 1 goes here, 2 goes here, 4 will go here. And I get 1 to 2 to 3, which is S. How was that? Any more questions about that one? Good. Okay. All right, B. B is an interesting one. So B has 2 hydroxyl groups down at this end. We have a wedged methyl group. We've got some carbons hanging off the end here. All right, so we have two areas where we have some stereochemistry indicated. However, how many stereocenters, let me say that a different way, how many asymmetric carbons do we have? We only have one. This carbon here has two hydroxyl groups attached, so that's not an asymmetric carbon, but we do have one here. So I'm going to draw the last group in, which is not shown, which is the dashed hydrogen. And now I'm going to assign priority. So attached to my asymmetric carbon is 1, 2, 3 different carbons and a hydrogen. So I have 3 ties in my hydrogen. My hydrogen's in the back at number 4. Okay. My methyl group, the carbon that's pointing is wedged, is a carbon that has 3 hydrogens attached. If I go to the carbon on the right, that one has 2 hydrogens and a carbon attached. Good. And if I go to the one on the left, that one has 2 hydrogens and a carbon attached. So we still have 2 that have a tie, right? But we can say that the methyl group, the one that I've now has a green dot on it, is going to be the lowest priority of all of those. So I'm going to give it 3. So we have a tie. So now we're going to go out one more. So now attached to this blue carbon, we have an oxygen, and an understood hydrogen. So we have 2 oxygens and 1 hydrogen attached to that carbon. For the purple carbon here, I have 2 hydrogens and a carbon. They're different. Who has the heavier atom? That's going to be the one with the oxygen. So the blue chain or the blue portion gets priority 1 and the purple priority 2. Okay, lowest priority is in the back, which is fabulous because we can just use our normal rules. So we have, let's see, 3, 1, and 2. So we go from 1 to 2 to 3, and that is R. Good? Sweet. Okay. 1 asymmetric carbon means that we are automatically a chiral molecule. Good, good. Okay. No questions? All right. So no questions? Checking the chat too. All right. Want me to go on to the next one? Okay. Let's go on to the next one. Here we go. So I was a little bit meaner on this one. I'm sorry. So this one is actually an eclipsed conformation with respect to the 2 that are in the plane. We have a hydroxyl group on the wedge and a dashed methyl group. Okay. So let's see, we have 1 asymmetric carbon, and attached to that asymmetric carbon is an oxygen, deuterium, carbon, and carbon. So highest priority is going to go to my oxygen. Lowest is my deuterium. Oh, I just wrote number 2. Sorry, number 4. Okay. We have a carbon here as part of a methyl group, which means it only has 3 hydrogens attached to it. The other carbon over on the right-hand side has 1 nitrogen and 2 hydrogens. So we have a difference. So the one with the nitrogen gets higher priority. So this is now going to be priority 2 because we already have priority 1. And the methyl group gets priority 3. So right now what I'm seeing is this. Priority 4 is pointing down. Priority 2 is up to the right. My priority 1 is wedged and my priority 3 is dashed. Okay, with me here? So I need to put my lowest priority group in the back. Right now, it's in the plane. So I need to basically make this fall over. Hold on 1 second. Gonna grab. Okay. I'm gonna really quickly attach my 4 different groups here, because I want you to see the motion that I did on this. Okay. So right now, our lowest priority group is pointing straight down, right? So this hydrogen here, or this deuterium that I have pointing down, is my lowest priority group. So what I basically want to do is take this asymmetric carbon and turn it like this. Okay. So what was wedged is going to be kind of pointing down. What was dashed will be pointing up. And what was pointing up to your right will still be pointing off to the right. Do you see what I did? The motion I did? Put it back like that. So if I do that, oh, that's not a pen. Choo, choo, choo. My carbon number 1, which is pointing out at you, will now be pointing down and to the left. So here's 1. Our priority 3 that was wedged away from you will now be pointing up here. And priority 2 that was off to the right will still be off to the right. Okay. That's all I did, was I just took my molecule and put it like this. So this might be a great example of why using a model set might be helpful if it works for you. Okay. So now we go 1 to 2 to 3, and we get S. This was a really commonly missed one, so I want to just pause here and see any questions on that. Okay. We have 1 asymmetric carbon, 1 asymmetric carbon. So therefore it is chiral. Cool. All right. D. Does anybody want me to go through D? That one you guys did pretty well on. If you do, if you want to just give me a little thumbs up. If not, I'll skip that one for now. Okay, so let's go to E then. E is the doozy because we got 2 asymmetric carbons in something that can rotate. So let's take a look at that one. So we have a alcohol, or 2 alcohols, which means we have a diol. We have a wedged deuterium and a dashed methyl group on the right, and on the left, we have a wedged methyl group and a dashed deuterium. Okay, so before we get this all cluttered with labeling it as our asymmetric carbons, let's go ahead and look for any plane of symmetry. Since we have free rotation, we need to look at different conformers to see if there's a plane of symmetry. One of our red flags for saying, there might be a plane of symmetry is because the asymmetric carbon on the left has the exact same groups as the asymmetric carbon on the right. Okay. So I'm going to take this and I'm going to see if I rotate. Oh, let me draw it a little differently. If I rotate around the central sigma bond, this one right here, so that I end up with the 2 OH groups reflecting in a mirror plane, I want to see what happens with the rest of the groups. Okay. So the group on the left, we didn't do any really rotation. This hydroxyl group stays there. So we have a wedged methyl group and a dashed deuterium. Okay, so let's see what happens with this deuterium. So let's pretend once again the deuterium is, hold on, I'm just orienting myself to what you're seeing here. So that should be, okay. So here's your deuterium. Okay, that's your hydroxyl group, right? Am I oriented right to you? Deuterium right now is pointing out at you, and the hydroxyl group is down to your left, down to your right, excuse me. I rotated so that the hydroxyl group goes up. Now the deuterium is pointed away from you and down. I'm going to go back here. Before we did the rotation, your deuterium on this carbon right here, your deuterium is coming out at you and is pointing up, right? This yellow is the hydroxyl group. I'm going to take this and I'm going to rotate it to show what I drew over here with the hydroxyl group pointing up. That deuterium is now pointing down and away from you. Okay. That is pointing down and away from you, which means it gets the dash. The methyl group, let's make that the red one, was pointing up and away from you. But when we did the 180-degree rotation, it is now pointing down and is wedged. Okay. So what do you think? Is there a plane of symmetry? There is. So this is a meso compound, which is achiral or non-chiral. Okay. If you are a big fan of the Newman projections, this is a great use of the Newman projection. Your original Newman projection would look like this. If we looked down this bond, we would have hydroxyl group up, methyl group down to the right, deuterium down to the left. In the back, we would see hydroxyl, deuterium, and methyl like this. If you rotate these groups 180 degrees, which is what we did here, let's keep the front the same. Let me move this a little bit over. Keep the front the same, deuterium, methyl. It's going to put the hydroxyl group behind the other hydroxyl group. Okay. If the back deuterium rotates 180 degrees, where does it go? Goes behind the other deuterium. If the methyl on the back carbon rotates 180 degrees, it goes behind the other methyl group. Now you can see when this is eclipsed, everything is reflected front to back. Can you see that? Yeah. Is anybody still working on Orgo? I understand people multitask during this. That's fine. Gotcha. All right. So I just want to show you some other kind of tools that you can use to visualize these and bringing back the Newman projections. All right, so let's go ahead and do RNS for this one. So I'm going to redraw hydroxyl, deuterium, methyl, methyl, deuterium. Okay, now we want to be careful about which groups we're going to compare. Okay, I saw this confused a few times, so I just want to go through this one slowly. On the left, here's one asymmetric carbon. Okay, attached to that is an oxygen, a carbon, deuterium, and another carbon. Okay. So from that, we can say that the oxygen is the highest priority group. The deuterium is the lowest priority group. Now we have methyl. So that's a carbon that has 3 hydrogens attached versus a carbon that has oxygen, another carbon, and a deuterium. This carbon has higher priority because it has the oxygen on it. Okay, so that is going to get priority 3. And the methyl group gets priority 4. Okay, so if we redraw it, you don't have to. We have 4, 3, 1, and 2. Right? Lowest priorities in the front. So we have to do the opposite rules. Oh, no,
Well,
sugar
this-
booger. I see what I just did. Sorry about that. I probably said it right and wrote it wrong. We said deuterium was the lowest. We said methyl was lower than the other carbon. Thank you. So let me just correct my numbers here. I remember looking at it before going, oh, this one's easier because the lowest priority is in the back, but good to go. So we go from 1 to 2 to 3, and that would give us R. Cool on that one? Yeah. Okay. Let's look at the other side. Other side, we have the same groups. So we can say priority 4 goes to the deuterium, priority 3 to the methyl, priority 1 to the hydroxyl, and priority 2 to the other group. Good. So that one, 3, 4, 2, 1. I draw that off to the side. Lowest priority is in the front, so opposite rules apply. 1 to 2 to 3 would normally give us R, but in this case, it's opposite, so it gives us S. If you don't like the opposite rules and you want to flip it over, the two that are in the plane switch places, 1 and 2, and the wedge dashes switch places. 3 comes in the front, 4 goes in the back. 1 to 2 to 3 gives us S. Good? Yeah, awesome. Questions, comments, concerns? Good. Okay. Okie dokie. So then the last one was the one I promised you would see something like it on there. And you guys did really well. I was so happy. Okay, so here we go. Do we have any asymmetric carbons? We do not. Okay, we have a plane of symmetry that goes right through the middle here. So we have no asymmetric carbons. We have a plane of symmetry. So this is achiral. I think you guys have done better than every class I've had before. So yay. I guess I've beat that dead horse for a long time now. Good? Yeah? Awesome. Okay. Any questions about this assigning RNS, determining if our molecule is chiral? Any questions with that? If not, what I want to do is walk through some sample problems that I would have given you as an exercise for next week, but I'm not going to because it's a light week. Okay. And I'm just bringing it here in front of me. And I will also, actually, let me shoot, I'm going to shoot the PDF in the chat in case you want to download it. I'll also post it on Blackboard later. This is what would have been exercise 5. It's not going in there, is it? One more time. It's coming, I promise. Move it to my desktop. Maybe that will help. File from my desktop. Exercise 5. Open. Okay. Can you guys see that coming through on the chat if you'd like to? Beautiful. Okay. So we're not going to probably walk through all of these so that you have some practice ones if you want to. But I thought we could start by walking through how to even attack these. All right. So the first part of the exercise is your favorite and mine nomenclature. And With this nomenclature, I really want to focus on going from the name to the structure, okay, as opposed to the structure to the name. So the first one that we have on here is S7 ethyl 7 methyl dash 3E comma 5Z parentheses dash decadiene. Anybody looking at this going, what the what? A little bit. Okay. So let's figure out how to attack this. Were you guys able to open the PDF in the chat? If you have, okay, beautiful, great. So we're not going to attack this any differently than we did before. We're basically going to start on the right-hand side of the molecule and we're going to move our way backwards, okay? And what I always try to do is save the stereochemistry for last, okay? So we have decadiene. So how many carbons are going to be in my main chain? We have deca, 10, right? So we have 10. Di means we have 2. Ene means we have 2 alkenes, okay? Where are those alkenes going to be? Well, they're going to start at number 3 and at number 5. So I'm going to go ahead and draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm just going to number down below here for my own sake. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Just so I know what side I started from. All right. So at number 3, I'm going to put the beginning of a double bond. And we're going to go back and check to make sure that's going to be E after I've added all the other substituents. Okay. So here we go. Here's carbon 3, and I'm going to add a double bond. Okay. At carbon 5, it's going to be my next alkene. It starts at carbon 5 and goes between 5 and 6. Okay. So we did the 3, we did the 5. We still need to check the stereochemistry. The reason I say wait till the end is because you can't really define E and Z or RNS until you have all the groups on here. Okay. So the next thing, on carbon 7, we have a methyl group. So on carbon 7, we have a methyl group. On carbon 7, we have an ethyl group. You're 99% done now. What do we need to do now? We need to figure out if we have the right stereochemistry on our asymmetric carbon that we just drew, and if we have the right stereochemistry on our alkenes. Okay, let's do our alkenes first. So here is carbon 3, or I'm sorry, the alkene that goes from 3 to 4. What are the highest priority groups on each end? Well, let's go ahead and draw the hydrogens in just to help us out. We look at this end and we have carbon versus hydrogen. Highest priority group, carbon. So our carbon gets 1, hydrogen gets 2. At the other end, on carbon 4, we have a hydrogen and a carbon. Carbon gets highest priority. Carbon gets highest priority. The hydrogen gets priority 2. If I pretend to draw a line down here so that I can just focus on one side, if the line confuses you, don't put it in. We just want to focus on one side. If we look at one side, do I have my 2 highest priority groups on the same side? No. As drawn, I put them on opposite sides, which means I drew the E. Is that correct? Yes. Okay. So I don't have to change this one at all. Now we're going to do the same thing for the other alkene. So here's my other alkene. And I'm going to draw in my hydrogens. All right. And let's take a look at this one. I'm going to look at the end on carbon 5. I have carbon versus hydrogen. So carbon gets 1, hydrogen gets 2. The other end on carbon 6, I have carbon, which gets priority 1, hydrogen gets priority 2. So if I focus on one side, do I have the highest priority groups on the same side? No, they're on opposite sides as drawn. Is that what I want? No, I want the opposite. Okay, so I need to do a little bit of a redrawing here. So we're going to, you can erase and redraw if you want. I like to redraw it. 8, 10, 2, 4, 6, 8, 10. Okay, carbon 3, I have my alkene. Oh, and on carbon 5, don't draw it just yet. On carbon 5, I need to change this so that the 2 carbon groups are actually on the same side of the alkene. So I need it to go up this way. So I'm going to need to have 1, 2, 3, 4 carbons there. Here's 1, 2, 3, 4 carbons. So this has gotten moved. And my alkene now is Z. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Carbon 7, I'm going to put back in my ethyl and methyl groups. Okay. And now we want to have this such that we have the S stereochemistry. So we want to make sure that we have the S stereochemistry. All right. Well, let's assign priority to the groups that we have. Oh boy, we got a whole bunch of carbons going on, don't we? So here's my asymmetric carbon. Attached to that is 4 different carbons that have 4 different groups attached to them. The lowest priority is going to be methyl. Okay. Because that carbon has 3 hydrogens attached. Let's compare this top one, carbon number 8 and carbon number 6. So the one on the top, this carbon has 2 carbons and a hydrogen. Carbon number 8 has, oh, sorry, sugar booger. You can tell it's Friday. The blue one up top has 2 hydrogens and 1 carbon. Carbon number 8 has 1 carbon and 2 hydrogens. And how about carbon number 6? What does that have the equivalent of attached to it?
2 carbons.
2 carbons and 1 hydrogen. All right. So the purple one's the highest priority group. That's going to get number 1. Okay. So how about the blue versus the pink? What's going to get a higher priority, the blue or the pink? Well, if we keep going down the chain, what we'll find out is that the next carbon on the blue one has 3 hydrogens. The next carbon on the pink one has 1 carbon and 2 hydrogens. So the pink is going to get higher priority, gets priority 2. And the blue one is going to get priority 3. Okay, so I'm going to draw just what we have right now off to the side here. I'm going to, little squiggle line means I cut it off. So what I have is 4, 3, 2, and 1. Okay. So we want this to be stereochemistry of S, right? We want that absolute configuration. So the question is, what is getting wedged and what's getting dashed on here? Well, ooh, just moved on me here. If we look and go around 1 to 2 to 3, 1 to 2 to 3, like this, normal rules apply, right? If number 4 is in the back, and that would give us S. I'm going to say that a slightly different way. If I assume that number 4 is in the back, that tells me I have normal rules applying, and that would mean that my wedged number 3 would lead to 1 to 2 to 3, which is stereochemistry, absolute configuration S. Does that make sense? If we wanted R, what we would have done is assume 4 is in the back. We would look and see, oh, well, this gives me S. So what do I need to do? I need to switch the wedge and the dash and actually make the methyl group the wedge and the other one the dash. So if we go back to our structure here, we would want the dashed methyl group and the wedged ethyl group. You could actually wedge any of the other groups. It really doesn't matter. I like to think of the 2 groups off the main chain as being the wedge and dash, but it really doesn't matter. So takes a little bit longer to work through that. Any questions on any part of that?
Yeah.
Yeah.
So could you not have a wedge on priority group number 2 because then it's like not in the V or something like that?
You would have to draw it in a different way. But I understand exactly what you're saying. So what you're asking is, if I drew this in exactly the same way and I put the wedge here and the dash here, like that, looks kind of weird.
Yeah.
Yeah, you would not want to draw it like that. You'd have to move things around in order for it to look correctly. So you would
Okay.
want to draw it with the ethyl group down and that propyl group up like this. That's a great question. Good. Is that changing things? No, that would change things. That would change things. You'd have to draw it from a whole different perspective. That's a really good question. So to simplify, thank you for asking that question. So let's just say this: to simplify, let's only put wedges and dashes on the substituents on the main chain. That'll keep you from having to rotate things around to put wedges and dashes in other positions. Great question. Thank you so much. So take that off. Good. All right. Do you feel like you could tackle the other 2 having done that one? Okay, good. I will say probably the most annoying thing is having to redraw it if you draw the wrong, or if your initial drawing of the stereochemistry of the alkene is the opposite to what it wants to be, and you have to redraw it. That's the most annoying part. All right, let's look at the next group. So in the next group, we want to determine if we have pairs of enantiomers, diastereomers, conformers, or if it's just an identical molecule. All right, so this is growing on what we were doing before with different isomers. But what the question is basically saying is, these are all going to be configurational isomers. They're stereoisomers. They're not going to be constitutional isomers. So let's take a look at the first one. So if we have a cyclohexane where we have wedge, dash, wedge, and we compare that with this one where we have a dash, a wedge, and a dash. How are we going to handle this one? Bless you. What do you think? Okay, so what can we do here to determine if these are anything? Anybody have any feeling? So one of the things you may want to start and look at is there a possibility that these are enantiomers? Is there a possibility that these are diastereomers? So some of the questions you can ask yourself is, if I compare the wedges and dashes on the left with the wedges and dashes on the right, are they exactly the opposite each and every time? They are, right? So even if I take this molecule, and I'm going to show you, and rotate it around like this so that it matches that one, can you see that every wedge and every dash is a complete opposite? So if every stereocenter is the opposite, this leads us to start thinking about whether or not they are enantiomers. But we need to caution ourselves because this could just be the same molecule flipped over. So one tool that you can use is ask yourself, is there a plane of symmetry? Is there a plane of symmetry? Okay. If there's a plane of symmetry, which there is in this case, there is one that goes right through the middle here, right through the middle here. That means that neither of these molecules are chiral. Neither are chiral. What does that mean? That means that it cannot have an enantiomer. Cannot have an enantiomer. But each and every stereocenter is the opposite absolute configuration when I compare the two. Try flipping it over in your mind. If I flip this one over, if I flip that one over, anything that was pointing up, and let me use a different word because I don't want you to do a chair flip. If I were to take this molecule and physically turn it over such that whatever on the top face is now on the bottom face and vice versa, kind of like a pancake when you make it, you flop it over, okay? We would end up with a molecule that looks like this, which is exactly the same thing as this molecule. So if I were to compare these are identical or the same molecule. Okay. So we want to make sure that we ask a couple questions and we don't jump right to the original thing that we felt, which was our impulse to say each and every stereocenter is of the opposite configuration. We compare the two, which would mean that they were enantiomers, but they're not chiral, which means they can't be enantiomers, which led us to they're the same molecule. Boom. Did your mind just go, you need a little break? All right, let's take a look at the next one. So I'm going to go to B. Okay. So I have this one. And I have gigantic version over here. Once again, not sure why I drew it that big. But here we go. Okay. Every asymmetric carbon, every asymmetric carbon, when I compare between the two molecules, this one and this one, opposite configuration. This one and this one, opposite configuration. Okay. So these are not diastereomers. So the question is, are they the same molecule or are they enantiomers? Okay, so all asymmetric carbons are of the opposite configuration. So the question is, are they enantiomers, TOmers, oh, sorry, or the same? Okay, so we're going to check and look for a plane of symmetry. Do we have a plane of symmetry? If I were to put a plane of symmetry here, do I have one? No, I don't, because of the nature of the stereocenters. This methyl group is pointing up at you, right? This one is pointing down away from you. So if we were to try to reflect through a mirror plane, they're going to kind of try to reflect like this, and it's not going to work. Okay, so we do not have a mirror plane. So if there is not a mirror plane, we have two asymmetric carbons. They are enantiomers of each other, because each of the asymmetric carbons of the opposite configuration. Okay, if I were, oh, that's not what I wanted. If I were to try to superimpose these two, can you see how they don't superimpose on each other? The wedges and the dashes don't line up. Okay, if I rotate it like this, you can see that these are mirror images. Okay, that are not superimposable. So those are enantiomers. Okay, so that means if this one is if this is R, then this must be S, and vice versa. That's also a way that you could check. Assign your absolute configuration to each of the carbons. I know you love doing that, and see if they're opposite. Okay. Good. Not good. Good. Okay. I'm going to skip to D because I want to give you C to kind of play with. But I want to jump to D. So here is D. So each of these is going to have an ethyl group and a chloro group drawn off of a butane. Okay. Oh. Okay. So we have, how many asymmetric carbons do you see? Do you see two? Two. Good. So we have two asymmetric carbons. Okay. We have one here and one here and one here and one here. When we compare the two molecules, are each and every single one of those asymmetric carbons of the opposite configuration? No, they are not. So if I were to, let me say that a different way. Right on this one on the right, you see they're both wedged. On the one on the left, one is wedged and one is dashed. Okay, so there's a difference in the relative stereochemistry. So not all asymmetric carbons. I always write as instead of asymmetric. Asymmetric carbons are of opposite configuration. So we have two stereoisomers where we have groups, we have asymmetric carbons where we have some that are different, but not all. So what do we call this group? I'll say that again. Enantiomers have each and every asymmetric carbon of the opposite configuration. If you look at enantiomer 1 versus enantiomer 2. Now we have a case where we have two stereoisomers, but the difference between them is that some asymmetric carbons are of the opposite configuration, but not all. What do we call those?
Diastereomers.
Good. Those are called diastereomers. So these are diastereomers. Diastereomers. Okay. So if I were to actually draw this one on the right, flip from the opposite perspective, looking from the opposite side, what I would see is a molecule that looks like this. Okay, I took that whole molecule and I physically turned it to the other side. We need another word for flip. So it's not like confused with a chair flip. So we took the molecule and flipped it over to its other side so that you can compare it directly with this one on the left. And hopefully what you can see here is that the chlorine, the asymmetric carbon that the chlorine is attached to is the exact same in both. That one's superimposable. But the asymmetric carbon with the ethyl attached is of the opposite configuration. One's wedged and one's dashed. Okay, so the one with the ethyl group, that asymmetric carbon is opposite configuration. The other one is the same. Because not all of them are the opposite, it's a diastereomer and not an enantiomer. It's the most unsatisfying definition. I totally agree with you. But I see some question marks, and I'm not sure if they're like exhausted question marks in eyes or just like question marks. Any question on that one? Okay. Do you feel like you have a couple tools to kind of attack these? Okay. Good. Okay. So let's talk about some of what we covered this week. In addition to the stereochemistry, we started talking about reactivity and relative reactivity. So for I'm going to skip number 3, unless you would like me to talk about it. So number 3 looks at a number of bonds and asks you to rank from the largest to the smallest dipole. Is everybody looking at a copy of it right now? Okay. Do you want me to walk through one of those? Or do you, yeah, walk through one? Okay, let's walk through one. Let's walk through A. So we're comparing the FH bond versus the NH bond versus the OH bond versus the CH bond. Okay. So if we're comparing those 4, we want to go from largest to smallest dipole. So the bigger the difference in the electronegativity, the bigger the dipole. Bigger the difference in electronegativity, bigger the dipole. And does everybody understand what dipole means with regards to charges? The bigger the dipole, the bigger the partial charges on the atoms. So the bigger the dipole, the bigger delta plus or delta minus on the atoms that are on either side of that bond. Okay. So you can look up the electronegativities. I am more than happy to put up the periodic table I have with the electronegativities written on there. But there are 4 that I would kind of put into your mental database here, which is your top 4 electronegative atoms and the order. Okay. So the most electronegative atom is fluorine. So this is our most eneg. Okay. Which is greater than oxygen, which is greater than, and I'm going to group these 2 together, nitrogen and chlorine. Okay. Because they're super close, the nitrogen and the chlorine. All right. But where these 4 are relative to each other is going to be really important. So if we look back at our bonds here, we have fluorine and hydrogen, nitrogen, hydrogen, oxygen, hydrogen, and carbon and hydrogen. So the hydrogen is constant through all of this, right? So the only thing we need to really compare is the electronegativities of those other atoms, because hydrogen's going to stay whatever hydrogen is. Okay. So fluorine is the most electronegative. So that means the difference between its electronegativity and hydrogen is going to be the largest, right? Yeah. Okay, so this is going to be the biggest difference in electronegativity. Ooh. All right. If that's the biggest difference in electronegativity, then that means it's going to have the largest dipole. So we're going to give that a number 1. Okay. The next most electronegative atom is oxygen. So the difference between oxygen and hydrogen will be the second greatest, and that gets 2. Nitrogen is third, so that's going to get 3. And lastly is carbon and hydrogen. And we spent some time talking about how those are virtually the same, really, really close. So this is almost nonpolar. Well, it is nonpolar, I shouldn't say kind of, but it is. Okay, is that helpful? At least on how to attack it? Okay. So I'm going to leave you with the circle the reactive parts because I think you guys are pretty good with that. But let's just talk about what we're looking for. Let me take a sip of water because my voice is going out. Excuse me. It wasn't what was my iced coffee. Wasn't what I was expecting. Okay. So what are we looking for reactive parts? We're looking for reactive parts. We're looking for where there's any charges, whether they're small, little, tiny partial charges or full ionic charges. We're looking for charges. Okay. And what you'll become more accustomed to seeing is those are going to be your functional groups too. Okay, so kind of keep an eye out for those. All right. So that being said, we're looking for charges, whether or not they're partial or they're full charges. Anything along the spectrum. Okay. So we just talked about how to find those charges. Those charges are going to result from bonds where the 2 atoms have, like over here, differences in their electronegativity. All right. Questions about that? Good. Okay. So let's take a stab at the next one. So put a little X in front of B because B, we did not get to that yet. That's going to have to do with resonance. And that's the one part that we haven't gotten to. So you could even put a note next to that for yourself if you want to. But let's take a look at the first 3. So we have oxygen with a minus charge, nitrogen with a minus charge, and carbon with a minus charge, which means they all have at least 1, if not 2 or 3 lone pairs on them. Okay. So we want to identify which of these is going to be the most, middle, and least reactive. So if we're talking about reactivity, that's directly related to how stable it is. So we're looking at reactivity and stability. So with these 3, the commonality between them is that they all have a minus charge on them, right? So we want to ask ourselves, what is stabilizing the minus charge? Okay, what is going to make one of these atoms more stable with the minus charge on it than the others? So nitrogen, oxygen, and carbon are all in the same row. So we're going to compare atoms in a row. So does anybody remember what the most important factor is if you're looking in a row? Oh, that's not a row, that's a column, in a row.
Electronegativity.
Good, it's electronegativity. If it's in a column, then we're going to look at size. So we're going to compare electronegativity. So look at electronegativity. Okay, good. So most electronegative is the oxygen. Most electronegative. This carbon is the least electronegative. and the nitrogen's in the middle. Would everybody feel comfortable with that? Once again, that I'm pulling that just from our little list here of the 4. Excuse me again. Okay. So if oxygen is electronegative, what does that mean about how much it wants to have extra electrons around it? It wants it, thumbs up, doesn't want it, thumbs down. Not sure, you don't even have to vote. Okay, so if you have an electronegative atom, that means that that atom wants to surround itself with electrons. It's a greedy atom. It wants to pull all the electrons towards it. So the more electronegative, the more stable it will be with having extra. It's like, great, join the party. We're going to hang. We're cool. So the most electronegative is going to be the most stable with extra electrons. Okay. The opposite is true for our least electronegative atom. Okay. Our least electronegative atom is like, I'm not sure if I want that extra electron density on me. I don't have enough protons in the middle to help stabilize that. Okay. That's really a big difference between the more electronegative atoms, which have a lot more protons in the center, more positive charge to stabilize those. Carbon has less. So carbon's like, I don't have enough protons to really stabilize it, to make me really uncomfortable. So it's going to be the least stable. And I apologize. I give my atoms personality because it helps me understand how they're going to react. So if it helps you, that's great. So this carbon doesn't have a lot of protons in the middle, really uncomfortable having all these extra electrons around it. It's really unstable. So therefore, what's it going to mean about how quickly it's going to react with something, how willing it's going to be to react with something? It's going to be very willing because it wants to give those extra electrons up. So that means it's going to be the most reactive. Oxygen, on the other hand, is like, we got lots of protons. We stabilize all those extra negative charges around it. We're good to go. We're stable here. We don't need to react. So this is going to be the least reactive. And if you're like me and you kind of like to think about things on energy diagrams, our oxygen containing ion would be the lowest in energy. So this is energy. The nitrogen would be in the middle. And our highest in energy, which means it's the least stable, most reactive, would be carbon. Okay. So where are we kind of going with this? You guys remember doing reaction coordinate diagrams and thinking about things like activation energy? Did you guys talk about activation energy when you took Gen Chem? Don't worry, we're going to review it if it's very kind of low on your memory recall list. But imagine if these all wanted to go and make the same products. This one is foreshadowing here. This one at the top is going to have a much lower barrier to go over than this one might. And then what this one might. Okay. So being more stable means that you're going to have a higher barrier to go over to become reactive. Okay. That's foreshadowing. Right now, I want you to be able to at least be able to recognize where these would be relative to each other in energy, stability, and reactivity. All three kind of go together. Good. So once again, skip B. I will post this, do it whenever you want to do it. If you want to hand it in, you can hand it in and I'll take a look at it, but I'm also just going to post the key so you can take a look at it also. So you don't need to turn it in. Okay, any questions? Was this helpful to go over this ahead of time? Okay, good. Good. All right. Well, have a great weekend. And I'll touch base with you later on today. I'll shoot an email out letting you know like what we'll do as far as next week is concerned. And once again, I welcome any additional input you have or thoughts. I really do appreciate it and have a good one. Bye, everybody.
Thank you.
Thank
Take
you.
care. Bye-bye.
Thank you.
Oh, you're very welcome. Take care.